Assalamu alaikum rahmatullahi wa barakatuhu. Some of you might have heard of a famous photo taken in April 2019 of a black hole. And looking at that photo, you may have been disappointed at black holes. This photo may not look nearly as cool as the renderings of black holes that we make, but in reality, a black hole is far cooler than just its image. First, let's talk about a quick overview of my presentation. First, we will discuss about what are black holes, what are the parts or the structure of a black hole, the creation and the lifetime of different types of black holes, and the effect of black holes on time. Beginning with what are black holes. A black hole is a region in space in which the gravity is so strong that even light cannot escape it. Contrary to its name, a black hole is anything but empty space. Rather, it is a great amount of matter packed into a small area. Imagine an object which has the mass of 10 suns but is squished into a sphere the size of New York City, resulting in a gravitational force so strong that nothing can escape it. Whenever anything ventures too close to a black hole and passes the event horizon, be it a star, planet, or spacecraft, the object will be stretched and compressed through a process known as spaghettification, meaning all of its energy is absorbed into the black hole. Black holes were first predicted by Albert Einstein through his theory of relativity, which predicted that a sufficiently dense mass can deform space around it to form a black hole. The term was first coined in 1969 by American scientist John Wheeler. Structure. There are a few main parts of a black hole. The core or the whole part of a black hole, or the black hole itself, is the singularity. This is where matter has collapsed into a region of infinite density to form the singularity of a black hole. All matter and energy that a black hole consumes ends up in the singularity. To create a picture of a singularity, imagine a 3D world with a hole in the middle from which the object falls through. The event horizon is a radius around the singularity from which matter and energy cannot escape. This is dubbed the point of no return. Basically, if you look at the black hole, the black part is actually the event horizon, which surrounds the singularity. The next part is the accretion disk, which is a disk of superheated gas and debris, which rolls around the black hole at immense speeds, producing electromagnetic radiation, which reveals the location of the black hole. Some of this material enters the black hole, while others are forced out to create jets. Although the black hole itself is dark, photons are emitted from hot plasma nearby in disks and jets known as a photon sphere. In the absence of gravity, these photons would usually be in straight lines, but just outside the event horizon, the gravity is so strong that light bends into a circular shape around the dark shadow. It is important to note that the shadow we see is not the event horizon. The event horizon is at the center of the shadow. The remaining shadow is simply where light is being curved and entering the event horizon. When a black hole feeds on star or dust, or any celestial objects in that matter, this consummation process produces jets or particles and radiation blasting out of the black hole poles at near light speed. These are called relativistic jets, and they can extend for thousands of light years into space. The inner edge of the accretion disk is called the innermost stable unit, and it is the last place that material can orbit safely without falling past the point of no return. Creation and lifetime. There are three main types of black hole, and each of them lives slightly different lives. The first and smallest type of black holes are primordial black holes. Primordial black holes are the smallest black holes and some of the smallest and oldest objects in the universe, older even than atoms. These black holes were formed just after the Big Bang, when as a result of the violent energy around, any tiny pocket slightly denser than its neighbors could become a black hole. The oldest primordial black hole that could exist would weigh 1 trillion kilograms, yet no bigger than a proton. Primordial black holes, being so small, make them very difficult to find, and their existence has not yet been confirmed. But it is possible that they could also be the very mysterious dark matter that holds the universe together. Most black holes are stellar black holes, which form from the remnants of large stars which die as a result of a supernova explosion, which is basically the explosion of very large stars. Only the large stars become black holes, while smaller stars become neutron stars, which are not as massive and they cannot trap enough light. The more that these black holes consume and merge with others, the bigger they become. It is also important to realize that a black hole does not suck objects in as a vacuum. Objects simply fall into it due to the immense gravity. As we were talking earlier about a singularity, imagine a hole in the 3D dimension where material falls into it. If our sun was replaced by a black hole, nothing much would change, except for the fact that we would, of course, freeze to death. These types of black holes are known as stellar black holes. It can be demonstrated theoretically that no force can protect a star from collapsing under the pull of gravity. If the entire mass of a star is great enough, or about 3 times the mass of our sun, it becomes a black hole. However, something unexpected happens when the star explodes. As the star's surface approaches an imaginary line known as the event horizon, time on the star slows in comparison to time measured by observers far away. Time stops when the surface hits the event horizon, and the star can no longer collapse, and it becomes a frozen collapsing object known as a black hole. Another way that a stellar black hole can be made is by the merger of 2 large neutron stars, as this merger would generate enough gravity to compress the mass on itself, albeit being some of the smallest mass black stars. On the other hand, supermassive black holes, which are responsible for keeping galaxies together, such as Sagittarius A, which is at the center of the Milky Way galaxy. The creation of these black holes is a mystery, but the most accurate theory is that of quasi-black holes. It is unsure as to if quasi-stars existed, but if they did, that would explain how such big stars came to be. Quasi-stars were stars which were thousands of times larger than our sun and gave birth to huge stellar black holes at the end of their lifetime, which merged and feeded to become even supermassive black holes. The first black hole picture ever taken that we showed at the beginning of the presentation was that of a supermassive black hole, which sits in the galaxy Messier H7. Supermassive black holes can grow to become ultramassive black holes so massive that their gravity becomes the engine for quasars, an accretion disk shining brighter than thousands of galaxies, and even have supermassive black holes which orbit them. These are the single largest objects in the universe, dozens of billions of times the size of our sun. But no matter how massive black holes are, they will eventually evaporate and die. This occurs through a process known as Hawking radiation. Over time, black holes slowly lose particles due to the endless cycle of virtual particles coming into existence and annihilating each other. As this process happens near a black hole, the black hole retains one particle while the other escapes and becomes a real particle, after escaping the so-called empty space of a black hole. In the beginning, this process is very slow, but as a black hole gets smaller and smaller, this process speeds up, and at the end of a life, of its life radiates away at the heat of thousands of nuclear bombs exploding, and eventually the black hole evaporates out of existence. Now let's talk about the effect of black holes on time. This is a very interesting topic. So it is impossible to talk about black holes without talking about the time dilation related to it. To begin, let's first talk about Einstein's theory of relativity. Einstein argued that as you get closer to any massive body, including the Earth, time slows down compared to the flow of time far away from that body, or compared to the flow of time for someone who is not being affected by the gravitational force of that body. His theory showed that gravity is not a force, but the curvature of space and time caused by the mass and energy of a certain body. It showed that time and space are not fixed and can be distorted by immense gravities. In fact, on Earth, this effect has been confirmed using sensitive instruments, albeit very minimal. Time slows down on our Earth compared to outside observers. For example, you would age 1/1000th of a second less at sea level than at Mount Everest. But near a black hole, the slowing of time is extreme. From the point of view of an observer outside a black hole, the object entering the black hole seems to freeze in time, as if someone has pressed the pause button for the time for anything at the edge of the black hole. While from the perspective of the person or the object on the edge of the black hole speeds up. In 1 minute, they would see the rest of the universe age 700 years. Well, of course, these numbers depend on the mass of the black holes, and this is simply an estimate, but meaning that 1 year at the edge of a black hole is equivalent to 700 years on Earth. It's like a one-way trip to the future, but like a one-way trip, there's no coming back if you manage to stay within the innermost stable orbit of the black hole, or else we'll simply be sucked in. Well, that is the end of my presentation, and thank you to all listeners. Goodbye.